Good afternoon, everyone. Thank you, organizers, for this opportunity to present at this conference. So here I'll present something that we work on right now within the project of making single-photon sources within hexagonal boron nitride using femtosecond laser approach. And the single-photon sources are to be used for quantum key distribution applications. So this is a collaborative project, including several international partners, both experimental technology and theorists. So single photon sources generally find quite a few use cases in quantum technologies, and here we focus mainly on quantum key distribution. So I think this graph nicely illustrates one of the possible scenarios how various cryptographic systems, how their security and probability for breaking them might evolve over time. So what we presently use, RSA, ECC, as is well known, it seems just to be a matter of time before quantum computers reach a certain compute power to break them, and they will become outdated. Post-quantum algorithms that are being implemented and tested right now, these nevertheless are still not tested by time against classical or quantum, and so quantum key distribution seems to remain one of those fallback and options, and might become more important and widely used in the future. So European Union is carrying out quantum communications infrastructure deployment, so with the nations and cross-border quantum key distribution networks within EuroQCI project. And this network is believed to form a backbone in the future for quantum internet that should connect quantum computers, distributed quantum sensors, etc. So here we focus on the transmitter part of these technologies. So the BB84, that's the standard QKD protocol used in both commercial and many laboratories. So Alice chooses two random basis, Z or X, to encode the secure key to be sent to Bob in these basis states. So this protocol is provably secure. It doesn't strictly require photon indistinguishability, simple prepare and measure sort of protocol. So when designing quantum transmitter, there's several considerations, whether it's going to be used for fiber communications, for free space. That depends what kind of wavelengths we're aiming on. Then what type of degrees of freedom those Q is going to be encoded. So for free space, that's typically polarization, either time bin or phase encoding for fibers. And finally, the photon source. Coherent weak pulse sources or lasers, these are typically used in commercial devices. And on the other side, we also have single photon sources that many of them are still under development. So both types of sources have their advantages and disadvantages. Lasers, of course, they're feasible. Tech is well developed. Of course, the disadvantage is due to Poissonian distribution, multiphoton emissions, and the security loophole that need to be covered with decoy protocols. So true single photon sources avoid these things. However, the system complexity, at least now, goes up, and typically these things require low temperature operations. So there's several platforms that single photon sources are being developed on. For telecommunications bands, typically quantum dots perform the best. However, atomic defect-based platform is likewise gaining momentum. So here, atomic defects, typically in wide bandgap semiconductors. So these things can be addressed optically, magnetically. Some of the applications that these things find is in quantum sensing, for example, magnetic fields. Some people considering using them for small quantum registers, storing information in electron or nuclear spins. And here we focus on using them for single photon sources. And for this project, we're working with hexagonal boron nitride. This material gained a lot of attention lately, and some of the things that's nice about it is that, well, first of all, the single photon sources they work at room temperature, stable, high brightness. SPS, the emissions cover from ultraviolet all the way to near infrared. The disadvantage is that most of these emissions cannot be clearly assigned, or at least it's not known which type of atomic defects are responsible for them, apart from 2 or 3 in the UV range. So what we actually aiming here is for the visible range. Free space applications, and particularly for these, the defect configurations are not known. Other challenges, of course, is then integrating these things into devices using some kind of hybrid approaches, high Q cavities, etc. In this project, we're using several ways to make defects within boron nitride. One of what will mainly focus is femtosecond laser-based approach. To also use ion implantation, various combinations, etc. That's a full suite of techniques to kind of do this defect hunting and try to pinpoint which emissions are responsible for what configurations. Try to find ways how to make them reproducibly. So both experimental and density functional theory calculations, atomic resolution imaging um, to find useful things for QKD applications. So here some of the results using femtosecond laser, single shot pulses. So essentially what we're doing here is finding the threshold where we do not make too much damage to the lattice, but only produce atomic level single photon emitters. So these are confocal fluorescence scans of some of these damaged areas, and as we go towards the lower energy, essentially these damaged areas are no longer seen in confocal fluorescence scans. And then when we switch off that Raman lines that give all these backgrounds, single photon sources kind of emerge. So how the characterization sort of looks like. We do these measurements at room temperature. So here's an example of some of the defects that we're kind of zooming in on around 700 nanometers. So they show sharp zero phonon lines, small sidebands, phonon sidebands. There's Raman around 575. These defects typically show around 2 to 4 nanoseconds lifetimes at room temperature, linear polarization, most of them, and anti-bunching to confirm that this is indeed single photon sources. So if we look away from the zero delay, many of these defects in HBN actually show bunching around the zero delay. So the simplest kind of model to fit that is tree-level model. So that includes a third so-called shelving state. So the shelving state, where it comes about now, depends on the system, on the symmetry, right? For example, in NV centers, these ground excited states are spin triplets. The shelving state is spin singlet, and these transitions are spin dependent. In HBN, it's still not real clear how those are, but in any case, for QKD applications, long shelving times, of course, can limit QKD rates. So this part of the endeavor is defect hunting, identifying. So we realized that we can make quite efficiently these defects around 1.7, 1.9 electron volt ZPLs. And so we're trying to figure out what these actually are. So they have, most of the emission is concentrated in the zero phonon line. It's broadened due to phonon probably dephasing 5 to 10 MeVs. And these phonon sidebands is one of the fingerprints to kind of compare that with theory. So both the ZPLs can shift, and as well as phonon sidebands can shift in HBN due to strain, electric fields, other defects nearby, and of course that could be also different configurations. So this is one of the, I guess, fingerprints to look at. Some of the preliminary results on carbon related defect that that our theorists think that could be a feasible explanation for this. So the blue line is the fluorescence line shape calculated with DFT, and that's to be compared with the orange line. Where we see pretty nice matches with all these little phonon side peaks. So the one around 160 MeV, for example, here is coming from the electron phonon coupling to HBN bulk modes. High density of states around that. So these kind of things, I guess the first steps to identify which of these HBN defects could be useful for QKD applications, and try to figure out how to make them reproducible. So thank you so much.